Dear ladies and gentlemen, please let me take you through this presentation about the conference paper Comparison of Cone Calorimetry and FDS Model of Low-Density Fiberboard Pyrolysis. My name is Paulina Magdolenova and I am from University of Žilina in Slovakia. The main aim of the paper is to compare time to ignition evaluated in FDS model with a real bend scale experiment of tested material. The tested material is based on wood, which is thermally thick construction material and is widely used in various forms in different types of buildings, while its fire-resistant properties still remain a big issue. Wooden fiberboards, which were chosen for the experiment, are one of thermal insulation systems based on mostly renewable raw materials, very common in civil engineering these days. Different types of wooden fiberboards serve different purposes, where low-density fiberboards were chosen for this experiment as those are best known for their remarkable thermal insulation properties compared to other types. Chosen method for the bend scale experiment is cone calorimetry, which with igniter was used to estimate time to ignition of tested specimens. Simultaneous thermal analysis, known as STA, is conducted as well to provide input data for the numerical simulation, such as reference rate and reference temperature. STA integrates two measurement methods, thermogravimetric analysis and differential scanning calorimetry. Simultaneously to laboratory experiment, numerical simulation of cone calorimetry was carried out. Burning was modeled using the fire dynamic simulator known as FDS, which is widely used for CFD models. As the low-density fiberboard Steicotherm fiberboards were chosen, which are 6 cm thick and are made out of 3 layers, as you can see also in the figure. Boards were saved to 10 to 10 to 6 cm specimens as demanded for cone calorimeter holder with square of 100 cm squared surface area exposed to heat flux from the cone. The density of the specimens was measured to 110 kg to cubic meter. 4 thermocouples were placed in the central area of the exposed surface. Thermocouples were embedded approximately 3 to 5 mm deep in the surface to prevent them from leaping above the specimen. Several tests were conducted at different heat fluxes from 15 to 35 kW per square meter. Data collected from all thermocouples were averaged in order to reduce inaccuracies. Surface temperature is an output of the experiment that helps estimate the time of ignition. This is verified also by video records of each experiment. The cone calorimetry burning of samples was modeled as a numerical CFD model in FDS. At first, a numerical TGA analysis was carried out to provide reliable material and reaction inputs for cone calorimetry scenarios. Input data for TGA analysis in FDS were based on known fiberboard material properties and conducted STA experiment. Heat release rate per unit area and mass loss rate per unit area provided the base for numerical simulation parameters such as reference temperature, reference rate, and fraction values of reactive material components. Output and comparison of the STA experiment and the numerical TGA analysis is shown in figures. Heat release rate per unit area on the left and mass loss rate per unit area on the right. For numerical model, FDS version 671 was used. The created mesh measurements are 15 to 10 to 40 cm, which is divided into 5 to 5 to 5 cm numerical grid cells. The cone calorimetry heat flux is defined as external heat flux in the surface input data. To represent real experiment conditions, hot particle was modeled 2 cm above the sample surface to simulate cone calorimetry igniter. Overall, 5 scenarios were created with a variety of external heat flux according to carried out experiment. To predict the ignition time of the sample, devices measuring heat release rate and Mastle's rate were modeled. The start, or the point where the sharp rise of the HRR to time curve starts, represents the time of ignition. In the shown figure, results from the experimental measurements are shown. Average values from all experiments are plotted, and ignition is indicated using red dots for clearer visualization. Also, on the right, we can see the time of ignition in seconds for each heat flux used. Times of ignition vary from 8 to 68 seconds at different heat fluxes. Both temperature and times of ignitions appear to be an inverse proportionality with heat flux emitted from the cone calorimeter, which was expected and confirms validity of collected data. In this figure, results from modeled cone calorimetry are plotted as heat release rate values for all created scenarios. According to cone calorimetry heat flux, maximum HRR values are reached, meaning that the higher heat flux evokes higher values of HRR. Point where the HRR curve starts to rise from zero value represents the ignition time of the sample. That is why a zoomed-in side is provided also in the figure. The zoomed part of the figure shows the beginning of the measurement, displaying the first 25 seconds, where it is easy to determine the time of ignition points for all scenarios, which vary from 3 to 30 seconds. Comparison of experiment and model results shows us quite significant differences in these approaches. Ignition times estimated from the model acquire distinctly lower values compared to laboratory measurements. Differences in results are inversely proportional to heat flux used, increasing in ignition time with lowering heat flux rates. Results are shown together in the table. According to gathered outcomes, we can see that in this case, FDS model doesn't correspond to laboratory experiment. Reaching the difference of 55 seconds in ignition time at 15 kW per square meter heat flux only highlights unacceptability of the model as a whole. Cone calorimetry of wooden material is therefore not reliable for FDS models. High inaccuracies might be caused by limited possibilities in material defining of the model. Besides cellulose, which was the only one defined as a fuel in the model, there are also other substances contained in the wood. One of the other substances is, for example, lignin. However, FDS failed to run a simulation with lignin chemical formula defined as fuel. Now, at the end of the presentation, let me thank you for your attention. If you have any questions, please contact me on this email address.